Okay, so a vector is a quantity that has two things. It has a magnitude and a direction. And so maybe the easiest way to see what a vector is just think about some examples. So some examples of vector quantities are forces. So if I apply a force to an object, of course it has a magnitude. I can have a greater force or a lesser force. But then it also has a direction. I can apply the same magnitude of force in different directions, and I'm going to get different results. Another example would be velocity. So if I go get in my car or my bike, whatever, I can travel with a certain speed. That would be the magnitude of the velocity. But then I also have a direction, and my direction may change. So my velocity is going to change. And so that makes it a vector quantity because it has a magnitude and a direction. So what about quantities that aren't vectors? Well, those would be scalars. And so some examples of scalar quantities would be temperature. So if I ask, what's the temperature outside? I'm just going to get a quantity, 28 degrees. And there's no direction in that temperature. It's just, that's the temperature. It's just a quantity. So another example of a scalar would be energy. So if I have an object, a ball or something like that, then it's going to have a certain amount of energy, whether that's in the form of kinetic or potential, but the quantity of energy it has nothing to do with any direction. So that would be a scalar quantity. Okay, so if we're working in some sort of coordinate system, so if we have, say, the xy plane, or this could be three-dimensional space, so we could also have a z-axis if we want to, then we can represent a vector quantity as an arrow. And now what we're going to use to describe vectors are lowercase letters like v with a little arrow on top. So this vector v is this represented in this coordinate system as an arrow, and it has components. So I can write the component vector in component form. And so to each coordinate axis, I have a component. So v has an x component, which I'll put v sub x. It has a y component, and it has a z component, like that. And of course, if I was just working in the xy plane, then maybe my vector only has two components. It would have an x component and a y component. But really everything we're going to talk about is the same, whether you're thinking about having three components or just two components. Alright, so let's say I have two vectors written in component form. And just for now, I'm just going to consider them in space, so having three coordinates or components. Everything we're going to talk about works the same if we just have two components. So now if I have another vector u that has its three components, then what I can do is I can add two vectors together. And this is really one of the most useful things about writing vectors in component form, is because it gives me an easy way to add them together. So to add two vectors, what do I do? Well, I simply add the components. So the new x component is going to be the x component of v plus the x component of u. The new y component, I'm just going to add the y components. And then the z component, just add the z components. And we can actually visualize this in terms of arrows. So if I have my vector v right here, and I have my vector u, so I'm going to draw them starting at the same point. That. So maybe I can think about this as some object, and I'm applying a force this way and a force this way. Well, then where is the resultant force going to be? So what I do is I just take a copy of u. So let me put my copy of u up here. So this is also u. Now the cool thing about vectors is that they really don't have to be based at any point. I can translate them and they're still the same vector. And then I can take my vector v and translate it over here and put it at the end of u, like that. This is still just vector v, I've just moved it over. And then the resultant vector is going to be the diagonal of this parallelogram that's formed right here. So this is going to be the vector u plus v in here. So in addition to adding vectors, I can also rescale vectors. And what I mean by rescaling is actually rescaling a vector by a scalar value, so making it either longer or shorter. So I can do that. So if I have a scalar c, so just a number, like 2 or 3 or whatever, and I multiply it by a vector, then what happens is that each of the components of v gets rescaled by this same scalar quantity, c. So if I double the vector, if I multiply it by 2, then all of the components just get multiplied by 2. So these are sort of the arithmetic operations with vectors. I can add vectors, and I can rescale vectors. So let's talk a little bit about the magnitude of a vector. So we said that the vector was a quantity that had a magnitude and direction. So let's first talk about the magnitude of a vector v. Well, this is also called, it's also called the length of the vector. So the magnitude of a vector v is also called the length, and it's denoted by these bars around the vector v, sort of like absolute value of v, but it's the magnitude of the length of v. And what is that equal to? Well, it's the square root of the sum of all of the components squared. And this is sort of coming from like the distance formula. So if I have a vector v here, and I have all of its components, so if it has, say, an x component, a y component, and a z component like that, then the length of the vector, and here I just mean really the literal length of this segment here that's making up the vector, is just given by the distance from this point to this point. In this coordinate system, the distance formula is exactly this. So that's the length of the vector. And this also gives me a way to talk about the direction of a vector v. And so what do I mean by direction? Well, I sort of mean the way that it's pointing, but to be more specific, the direction of v is going to be a unit vector. And what do I mean by unit vector? I just mean that it's a vector of length equal to 1, pointing in the same direction. So how do I find this direction vector of v? Well, I'm going to denote it by v, and then I'm going to put a little hat over v. So v hat is just going to be v, so that gives me the direction, and to make it length 1, I just divide by the length. So the direction of v is this vector where I take v and I divide by the length of v. And so the nice thing about this notation is that any vector v can always just be written as its length or magnitude times its direction, like that. Example gives us two vectors, and we want to find all of these things. So first, we want to find the length of u. Well, the length of u, remember, it's just going to be the square root of the sum of the squares of the two components. And so this is going to be the square root of 3 squared plus 4 squared, that's 25. And the square root of 25 is 5. So the length of u is 5. So next, we just want to find u plus v. Okay, but we know how to do that. We just add the components. So we take 3, and then we're going to subtract 1. And then we take 4, and then we add 1. And so we'll get 2, 5. Alright, so next, we want to find u minus v. So this time, instead of adding the components, we're going to subtract the components. So we're going to have 3 minus negative 1, and then we'll have 4 minus 1, and that'll give us 4, 3. Alright, so next we want to take the quantity 2 times u plus 3 times v. And so this time, what two vectors are we adding? Well, we're adding twice the vector u, but twice the vector u, we just double each of the components, so that's 6 times 8. And then 3 times the components of v. And then we add this together, component-wise, and we just get 3, 11. And then finally, for the last part, we want the magnitude of u minus 2v. Okay, and this is going to be the magnitude of, well, I'm going to take 3, 4, and I'm going to subtract twice v, so that's minus 2, 2. Okay, and this is the magnitude, so I'm just going to go ahead and do this difference. So that's going to be 3 minus negative 2, so that's 5. And then 4 minus 2 is 2. So we just want the magnitude of this vector 5, 2. But that's the square root of 5 squared plus 2 squared, which is the square root of 29. With these two vectors, u and v, and now notice they have 3 components instead of just 2, so these are vectors in space, not just in the plane. So first we want the length of u. Well, again, this is just the square root of the sum of the squares of the components. So 1 squared plus 2 squared plus 2 squared is 9. So the length is just the square root of 9, which is 3. So finding u plus v, well, this is exactly the same as before. We just add the components. So this will be 1 plus 1, 2 plus 0, and 2 plus 1, or 2, 2, 3. Okay, so now for u minus v, we do the same thing except we just subtract the components. So it's going to be 1 minus 1, 2 minus 0, 2 minus 1, or in other words, 0, 2, 1. Okay, and then for 2u plus 3v, we'll just take twice u, so 2, 4, 4, and then add 3 times v. So remember, just rescaling a vector, we rescale each component. So 3, 0, 3. And this is 5, 4, 7. Just adding the components. Okay, and then finally we want the length of u minus 2v. So this is the same thing as finding the length of u, just 1, 2, 2, and then subtracting twice v, which is 2, 0, 2. But this is the length of minus 1, and then 2, and then 0. But this is just the square root. Once we have it in component form, it's just the square root of the sum of the squares of the component. So minus 1 squared plus 2 squared plus 0 squared. But that's just the square root of 5. We have these two vectors, and we want to find a unit vector pointing in the same direction. Or in other words, we want to find the direction vector. So if you recall, the direction vector is just the vector divided by the length. So the first thing to do in both cases here is to actually find the length of the vector. So what is the length of the vector u? Well, this is going to be the square root of 12 squared plus negative 5 squared. So that's 144 plus 25 gives us the square root of 169, which is 13. This is kind of a famous Pythagorean triple. Okay, and then the direction of u, so u with this little hat, which will take to mean the direction of u, is going to be u, the vector u, divided by the length of u. Okay, and then this is just going to be, well, I'm just rescaling each of the components. I'm rescaling the vector u by 1 over the length of u, so that's just rescaling the components. So this will be 12 over 13, and then negative 5 over 13. All right, and then we can do the same thing for this vector v. So we'll start by finding the length of v, which is just the square root of 1 squared plus 1 squared plus 1 squared, which is the square root of 3. And then the direction of v, so v hat, is going to be v divided by length of v, but dividing the vector by the length of v is the same thing as just dividing each of the components of v by the length of v. So 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. Okay, so a plane is flying 30 degrees north of east at 500 miles per hour, so this way. That's what this vector is representing. And then it encounters a jet stream that pushes it due south at 20 miles per hour, so that's this vector this way. And so what is the new speed and direction of the plane? Okay, so if we recall, we can actually find the resulting vector from this picture. So we can just copy vectors like that. So our new vector will be somewhere out there. I mean, that may not be to scale, but that's kind of the idea. I have a vector going this way and a vector going this way, and then the resultant vector is going to be out there. So I just want to add these two vectors together. And I want to utilize sort of this underlying coordinate system. So if I just have my standard xy plane coordinates, then what I have is I'm adding the vector, well, this 500 miles per hour has a component in the horizontal, which is 500 cosine of 30, and then a component in the vertical, which is 500 times sine of 30. This is a right triangle right here. And I'm adding this other velocity vector, which is only in the vertical. It has 0 in the horizontal, and it's actually negative 20 because it's pointing down. So my velocity vector is just going to be the sum of these two vectors, which is going to be 250 times the square root of 3. So I just use my values for cosine 30 and sine 30. And this is going to be 250 minus 20, so 230. So there's my resulting vector. And now the length of this vector, so my new speed, is just going to be the length of this vector. Which we can just throw in our calculator, which is 20 times the square root of 601, which, well, that's approximately 490.306 miles per hour. And then our direction, so we can either just normalize this vector, but it might be a little bit better to sort of say it as an angle, north of east or south of east or whatever it is. And so the angle, just a little bit of trigonometry, is going to be the inverse tangent of 230 over 250 root 3. So tangent is opposite over adjacent. And this gives us, well, approximately 27.9756, and this is degrees, and it'll still be north of east. Okay, so we have this light suspended from a ceiling by two ropes. And you can see the angles that they're making with the ceiling up here. And there's a tension in rope 1, there's a tension in rope 2. And so if we think about this in terms of components, well, the light is going to be applying a force down. It's going to want to fall. This is really due to gravity. So there's a force of 50 pounds down. T2 is going to be pulling the light this way and then also up, holding it up. T1 is going to be pulling the light this way and then also pulling it up. So the light is what's in what's called static equilibrium. And so all that means is that all of these arrows are balancing out. So the horizontal arrows have to equal each other, and the vertical arrows have to equal each other. And so what we want to do is use a little bit of trigonometry here. Notice that these are right triangles, so the horizontal and vertical components of T1 and T2 we can find with just a little bit of trig. And so if we add up T1, T2, and then the weight of the light, we should get 0. So we can represent that as, okay, so if we start with T1, the horizontal component of T1 is going to be negative, because it's pushing to the left, 15, it's the angle, whatever T1 is, and then cosine of 15. So remember, we're actually looking for T1, but whatever it is, to get the horizontal component, we just multiply by cosine of 15. And then the horizontal component is T1 sine 15. And it's positive because it's pointing up. And then we can add T2. So same thing, this time the horizontal is going to be positive, but it'll be T2 times cosine 25. And then the vertical will be T2 sine 25. And then we'll add in the weight. So the weight is just going straight down. So there's 0 force in the horizontal, and there's negative 50 pounds in the vertical, because it's going down. Okay, and then this should equal 0, 0. Well, why should it equal 0, 0? Because we want there to be 0 net force. So this is just adding up all the forces as vectors, and the net should be 0, 0. And so what we get is we get a system of two equations and two unknowns. So if we just kind of add all of these horizontal components, they have to equal 0. So negative T1 cosine 15 plus T2 cosine of 25 plus 0 has to equal 0. And then also T1 sine 15 plus T2 sine 25 minus 50 has to equal 0. And this, again, is just a system of two equations, two unknowns. I actually just put this in my calculator. I mean, another way to do it is just to use substitution. So solve for, say, T2, and then substitute in for T2, or you can just set up a matrix. However you want to do it, it's just some algebra review. And so what you get is you get that T1 is about 34.4728 pounds, and T2 is about 36.7405 pounds.